Hello, this is Professor George Easton. In this video, I'm going to talk about the bias-variance trade-off, cross-validation, and overfitting in the context of prediction. So as an introduction, the situation we are considering is as follows. Suppose we have a set of data consisting of a dependent y variable and a set of x variables, just as you would have in a regular linear regression. But in this case, we're imagining that our dependent y variable could be some nonlinear function f of the set of x variables plus an error term epsilon, which plays the same role as the error term in a regular linear regression. Now let's also suppose that we have randomly divided our data into at least training and validation samples, and ideally we would have also included a final test sample as well. And finally, suppose that we have calculated on the training data an estimate of this nonlinear function f of x, which we are going to denote by f hat of x. So I want to reiterate that this x here, which I've written with a capital X, really represents a set of independent explanatory variables, just as you would have in a regular linear regression. So just to make this clear, if our f hat of x came from linear regression, then f hat of x would be equal to alpha hat plus beta hat 1 times x1 plus beta hat 2 times x2, and so on, up to beta hat p times xp, where these coefficients alpha hat and beta hat 1 to beta hat p are just the usual least squares fitted regression coefficients. In this case, these fitted coefficients, the intercept alpha hat and the slope coefficients beta hat 1 to beta hat p, are going to depend on the y values and the x values in the data that they're estimated from. And so what this means in this case is that our f hat of x depends on the training data. So if I were to use a more complete and thorough notation, what I would do is represent f hat of x as being dependent on the y training data and the x training data. But this notation is cumbersome, so I'm going to suppress the dependency on the training data here. But you know now that f hat of x really depends on the training data through the estimated coefficients. Now my example here has been based on linear regression because I expect that you are very familiar with linear regression. But remember, what I'm really thinking about here is that my function f hat of x is some nonlinear function of those explanatory x variables, and that it is an attempt to estimate some true underlying nonlinear function that relates those explanatory variables to the dependent variable y. Now before we get into the bias and variance trade-off, I want to remind you about what bias and variance are. Let's suppose that I have a statistic S. I'm just using the capital letter S here to represent some statistic which will be computed off of data. And let's suppose that this statistic S estimates some unknown parameter theta. So again, if I want to get specific to the case of regression, then the fitted regression coefficient beta hat is going to be estimating the true slope coefficient beta. Then the bias of our statistic S is going to be the difference between the expected value of S and the value of the thing that is estimating, the theta. So the bias of S is the expected value of S minus theta. Now the variance of the statistic S is just going to be the expected value of the squared deviation of the statistic from its mean. So what that means is that it's the expected value of S minus the expected value of S, that's its mean, and take that difference and then square it, and then take the expectation of that squared difference. That is the definition of the variance of S. So now applying these definitions to our function f hat of x, the bias of f hat of x is just the expectation of f hat of x minus the true f of x that it's trying to estimate. Similarly, the variance of f hat of x, just plugging f hat of x into the definition of the variance. The variance of f hat of x is just going to be f hat of x minus its expectation. You take that difference and square it, and then you take the expectation of that squared difference. That's going to be the variance of f hat of x. So I'm now in a position to give you the formula for the bias-variance trade-off. The formula is as follows, and I'm now going to explain each of the terms. The term here on the left-hand side that we're going to decompose into three terms on the right-hand side is the expected mean square error of the prediction on the validation sample. So the mean square error of the prediction is going to be the actual realized value minus the value predicted by f hat of x, and then you square that difference and take its expectation. So this is the expected mean square error on the validation sample. It's going to be equal to the variance of the fit. So this is the formula that I just showed you for the variance of f hat of x. So it's f hat of x minus its expectation. Take the difference and square it, and then take the overall expectation, plus then the squared bias. So the bias was the expectation of f hat of x minus the true value, which is f of x. And then this is squared. And then finally we add to that the variance of the error term epsilon. So this is the variance of the error, which we're going to assume as usual is sigma squared. Now I have a note here which is really mostly to myself. So y here is a new observation from the validation sample. F hat of x will be computed using the x from the validation sample, but the coefficients that define f hat of x will have been estimated from the training sample. Since the coefficients that define f hat are calculated from the previous y's that were a part of the training sample, the new observation y and the f hat of x are going to be uncorrelated. The x here used in f hat of x is the new x corresponding to this new y observation, but our analysis is conditional on this x, so it's considered a constant. Now it's not all that difficult to derive this formula, but I'm not going to do that here because I really don't think that it's all that useful. But what is important is the idea that the prediction mean square error, so this is the mean square error of the prediction on the validation sample, is going to be equal to the squared bias of the fit, that's a bias term, plus the variance of the fit, and then finally the variance of the error. Now this is sometimes said in kind of a shorthand way that the MSE is the bias plus the variance, and this is not quite right because it's really the bias squared, and in addition the variance of the error has been left off. But this is basically the idea, is that the major components of the prediction mean square error correspond to a bias piece plus a variance piece. Now on the training sample, the mean square error always goes down as the model f hat of x becomes more complex or has more parameters. And this is intuitive because the more flexibility you have in fitting the data, which is really what's meant by saying that f hat of x becomes more complex, but the more flexibility you have in fitting the data, the closer you should be able to come to a perfect fit of that data. But on the validation sample, things are different. On the validation sample, what generally happens is the mean square error will usually go down as the model increases its complexity, but only up to a point. The mean square error is going down initially as you increase complexity because the bias is being reduced. But then the mean square error on the validation sample will start to go up. And it goes up because of the phenomenon of overfitting. And overfitting begins to occur when the model complexity gets sufficiently high that random features of the training data are being fit by the model. Well, this is a very important idea, and that idea is that the mean square error will initially decrease, but then increase on the validation data, even though the mean square error continues to decrease on the training data. And as I say, this is really a very important concept to understand. So now I'm going to make an illustration that shows what I've been talking about over the last few slides. So I'm going to begin with an x and a y axis. And on the x-axis, we're going to represent the complexity of the model we're fitting. And remember that complexity often corresponds to the number of parameters. And on the y-axis, we're going to put the performance of the estimator. And since we've been talking about prediction, that's going to be, in this case, the mean square error. Now, on the training data set, our models may start out performing not very well because they are not sufficiently complex to represent the structure in the data. So when the model is too simple for what's going on in the data, the model will fundamentally suffer from a substantial amount of bias, and it won't be able to perform very well. But as the model complexity goes up, on the training data, the performance will improve, and it will continue to improve as the bias is removed, because the model becomes sufficiently complex to actually fit what's going on in the data. But then it will continue even further, and eventually it's going to fit the data essentially perfectly. Now, it's typically going to be able to fit the data essentially perfectly when the number of parameters is about the same as the number of data points. Well, what happens on the validation data? Well, on the validation sample, you're very likely to start in essentially the same place if you're fitting a model that is too simple for the structure in the data. Then, as the complexity increases, the performance of the model on the validation data is also going to increase. But at some point, the performance on the validation data is going to start to taper off. And this happens when the complexity of the model is sufficient that there's essentially no bias. But then as you add additional complexity, what's happening is that the model is beginning to fit random noise in the data, and as a result of that, the performance on the validation data will decline. So this trace is for the validation data, and then this trace is for the training data. So the best possible model is the one that corresponds to the minimum of the trace for the validation data. It's going to be the model that has sufficient complexity that it's able to fit the structure in the data, but not so much complexity that overfitting is beginning to occur.
Now, before I go on, I want to make some comments about the problems of overfitting and of model selection in statistics. Traditionally in statistics, the sample sizes that we have been dealing with have not been so large that it's been particularly practical to hold out a validation and a test sample. As a result, the field of statistics has developed a number of goodness of fit methods that try to prevent overfitting of the data, all on the training data, and that is without a validation sample. So it's all done within sample. One example that I expect that you're familiar with is the adjusted R-squared in regular least squares linear regression. And as you probably know, the adjusted R-squared can be used to choose between regression models that have different sets of x variables. So the idea of the adjusted R-squared is that it penalizes adding in x variables that do not contribute anything to the regression. And this is different than the regular R-squared, which will continue to get better as new x variables are added into the model. So using the adjusted R-squared to try to pick the best model is intended to prevent overfitting, because the adjusted R-squared does not reward adding in variables that are not contributing in a meaningful way to the overall fit and are just fitting random noise. Now, another goodness of fit measure that is used in model selection and intended to prevent overfitting is called the AIC, which stands for the Akaike Information Criterion, and it is named after the professor that proved the main asymptotic result about this measure's behavior. But for the AIC, the smaller the value, the better. There's also a corrected version of the AIC that works better in small sample sizes, which is called the AICC. So like the adjusted R-squared, the AIC can be used to choose between models that have different sets of X variables. And I'll add here that the absolute magnitude of the AIC does not have a reasonable interpretation, so the usefulness of the AIC is to compare the values between models that have different sets of X variables. Now, the AIC and the AICC in smaller samples is probably a better method for model selection and to prevent overfitting than the adjusted R-squared. But overall, having a randomly drawn validation sample is a more direct test of overfitting. And when you do have enough data to randomly split your sample into a training set and a validation set, using the validation sample is probably better than using any of the in-sample measures. But do not interpret this to mean that these measures, such as the adjusted R-squared or the AIC or AICC, are not useful, because they are. I think they tend to be quite useful in terms of limiting the set of models that you fit on the training data set, and then you can go on to verify which one of those is best using the validation sample. So I've talked some about overfitting at this point, but now I want to address overfitting specifically. Now, when a model is fit to a data set that has sufficient flexibility, and here flexibility and complexity really are essentially referring to the same thing. But when that model has sufficient flexibility that it begins to fit random features in the data, it's said to overfit the data. When you have such a model, the bias in the model will typically have gone down because the flexibility is allowing that model to fit the main structural features in the data. But the variance will increase because the model is actually responding to the noise in the data, and it's actually fitting the noise in the data. So now, referring back to the bias versus variance trade-off, when you are overfitting the data, the bias will be low, but the variance will be high. And referring back to our y equals f of x plus a random error model, what's happening is that the fit will be picking up the noise in those error terms, and the residuals will be unrealistically small. So we've talked a lot about the validation data set so far, and we've mentioned cross-validation in passing, but now I want to address cross-validation directly. So in statistics, methods that split the data into training and validation data sets generally go under the name of cross-validation. So what we've been doing, which is just splitting the data into a training set and a validation set, randomly of course, is a form of cross-validation. So let me just clarify a little bit the difference between the first and the second bullet here. Many of the methods that go under the name of cross-validation in statistics involve splitting the data into training and validation data sets multiple times. What we have done so far is just take our data and split it into a training and a validation and perhaps a test data set as well, but just a single time. So when we split the data into a training and validation data set randomly a single time, this is really the simplest kind of cross-validation that we might consider doing. So let me just remind you of how you generally do your splitting of data in data science. In the context of data science, you're generally thinking about very large samples, and you want to split your data into a training sample, a validation sample, and then finally a test sample. Typical percentages for the various splits might be 50% for the training sample, 25% for the validation sample, and 25% for the test sample. Or you might split it 60% for the training, 20% for the validation, and 20% for the test. If you have a relatively small number of observations, for example, say 300, you might forego the test sample and just use a 2/3, 1/3 split, so 200 observations in the training sample and 100 in the validation sample. So now how do you use these samples? Well, the training data is used to estimate or fit a relatively small set of models. So for example, these models may be several linear regressions that have different sets of x variables, or they might be a collection of regression trees with different numbers of end nodes. Or you might compare regression trees to linear regression models. But when I say fitting, what is meant is the estimation of the parameters of these models. So for example, if one of the models is a linear regression, then calculating the fitted linear regression coefficients. That is the idea of fitting. Now the validation data set is used for a different purpose than fitting the coefficients. What the validation data set is used for is to pick which of the models that are being considered that were fit on the training data set is the best. And in the context of prediction, best is determined by which one of those models has the smallest error in predicting the y values on the validation data set. So the validation data set is really being used to determine the right level of model complexity, or equivalently, the right level of model flexibility. Now, the real power of cross-validation is that cross-validation generally prevents overfitting the data. Why does that happen? Well, the random noise or random features that end up in the training data set that are fit by a too flexible model are not likely to also be occurring in the validation set. Different random features may occur there, but those features won't have had any influence on the model fit to the training data set. So a model that overfits the training data set will generally perform badly for the validation data. And because of this bad performance in comparison to simpler models that don't overfit, the overfitting model will not be selected by the validation data. Now, once you've decided on your model, you can then, if you want, refit the model to both the training and the validation data, which will of course increase your sample size and therefore reduce the variation in your estimates. And then if you have a test data set, it can be used as a final check. So what I've been discussing here is one of the most important and central ideas in data science. So I want to summarize it again and make sure that I've clearly stated how you think about what's going on. The training data set is used to both discover and to fit, which means to estimate the model's parameters, a reasonably small number of models. These models typically should span a reasonable range of flexibility or complexity, because exactly how much flexibility you need to fit the structure of the model without overfitting is typically not clear just by examining the training data set alone. So the deliverable, the thing you should get out of the training data set, is a reasonably small collection of models together with their fits, which means estimates of their parameters based on the training data, that can then be tested on the validation data set. These models, which were discovered and fit on the training data set, then compete on the validation data set by predicting the y variable. So what this means is that the x variables for each observation on the validation data set
are plugged into these predicting functions to get a prediction for the y variable. You do not refit or re-estimate the parameters for these models on the validation data set. You just apply the models to the x variables to get predictions for the y variables. The validation data set then is used to pick the right model complexity and/or structure based on how well the models do in predicting the y values on the validation data set. So now, in conclusion, it is really hard to overstate the importance of using cross-validation in data science, and really any time that you have enough data that cross-validation is feasible. This problem of overfitting of the data is generally very much underappreciated. It's really not especially intuitive. And if you have enough data, cross-validation is easy enough to do. So you should basically always do it so that you get an out-of-sample assessment of whether or not the model that you are considering is in fact overfitting the data. And finally, there are other ways to do cross-validation, such as leave-one-out cross-validation or k-fold cross-validation, that I'm going to talk about elsewhere. The purpose of this video is to really clearly identify what the bias-variance trade-off is and to discuss how cross-validation prevents this problem of overfitting. In part 2, we're going to look at an example that will give you a very clear idea of what overfitting is and how cross-validation tends to prevent overfitting from occurring.